Hi everyone. This video is a continuation of part 1, so go ahead and watch section 4.7, part 1 if you haven't already. I'm not sure exactly where the video cut off, but I just wanted to mention for that first example there, the reason I wanted to show that to you was because we ended up with an all zero vectors here, so we had 2 degrees of freedom. And in that specific case where we have 2 degrees of freedom and this repeated eigenvalue here, in that case, since we get to choose whatever we want for our eigenvectors, we can just choose 1, 0, and 0, 1. So this next example that I'm going to show you is kind of what you'll be doing most of the time when you run into repeated eigenvalues. So this one, if we do the same thing to find the eigenvalues for this one, we'll end up with the same characteristic polynomial, so 2 minus lambda, determinant of 2 minus lambda times 2 minus lambda minus 0 is equal to 0. So we end up with the same result for our eigenvalues, that it's going to be a repeated value of 2. And we say this has a multiplicity of 2. And we can tell that because we have 2 of these, right? It's this 2 minus lambda squared, or it occurs twice in the characteristic polynomial. The 1 here is what's going to make this problem a little bit different, and it's going to cause some issues with us. So if we sort of proceed like normal and try to find our eigenvector, we can set up this equation. But I'm just going to let you know that we're going to run into some issues when we try to set up this eigenvector here. So if I write out a minus lambda I times x, I guess I can zoom in here, sorry about that. Right, so if I zoom in, if I write this equation a minus lambda I, then this is the matrix that I get. My bottom row says that I have a degree of freedom, and my top row here says that x2 is going to be equal to 0. So if I want to choose my eigenvector, I'll let x2 be 0, and I'll let x1 be equal to 1 so that I don't get a 0 vector. So that'll be the choice that I make. x1 is equal to 1. That means my eigenvector, the first one looks like this. So here's where you can run into the issue, and you might see it already. Normally, if we had 2 different eigenvalues, then we would just let this be our first eigenvector, and then we would use our second eigenvalue to come up with our second eigenvector. But in this case, we would just end up with the exact same thing if we plugged in, a minus 2 times the identity matrix. We would just end up with the same thing, and we can't do that, right? If we tried to have the same eigenvector for both of them, if we think about our Wronskian would end up being something like, let's see, e to the 2t 0, e to the 2t 0, right, for a y2. And this is going to give us a Wronskian, or determinant, that's equal to 0. And that means it's not going to be a fundamental set of solutions. So we can't do that. We also can't just do what we did in chapter 3, where we just write t out in front of the second eigenvector. Or that one's also not going to work because, again, we're still going to get a Wronskian that's equal to 0. That means we don't have a fundamental set of solutions, and that's just not what we want, right? We want to have eigenvectors that are linearly independent. Neither of them are equal to 0, and then the solutions that result from that, we want those to be fundamental set of solutions. Sorry. So I'll refer you to the book to see exactly why this is the case, but we can't find a linearly independent eigenvector x2 that satisfies this equation. So what we need is a new kind of set of eigenvectors that are going to be able to accommodate repeated eigenvalues. So just scroll down here. This is something you might want to write on a flashcard here, but we're going to call them V1 and V2. These are our new eigenvectors that can deal with repeated eigenvalues. The equations that we set up, the first one is going to be exactly what we would do normally for real eigenvalues. So that 1, 0 that we found above, that's going to work for this one. And then the next one we set for our second eigenvector, we set that instead of the 0 vector, we set that equal to the first eigenvector, V1. Again, for y1, we say that the first solution is e to the lambda t times our eigenvector. And then we can't just write t here, right? For the reason that I gave above, we still get a Wronskian that's equal to 0 if we do that. So our second solution is going to be t times our first solution plus, and then we'll use this second eigenvector. So this stuff that I've written in the orange here, this would be good to write down on a flashcard, just to say this is generally what you do if you have repeated eigenvalues. Okay, so let's try to use the system on that previous question that we looked at. So if I start with this first equation here, a minus lambda I times v1 is equal to 0. We get exactly what we did when we made our first attempt at this problem. Similarly, we can say that our first eigenvector is equal to 1, 0. The second equation says that we, instead of the 0 vector, we use our v1 eigenvector. So you can see we have a 1, 0 on the side here instead of 0, 0. This tells us that we have a degree of freedom on the bottom here, and that this equation tells us that v2 is equal to 1. So if v2 has to be equal to 1, I think the only real good choice here is going to be, if we want as many zeros as possible, we're going to choose v1, the value in this case, to be 0. So we'll get a second eigenvector that looks like 0, 1. So we have 1, 0, and 0, 1. If you refer back to the solutions in orange for y1 vector and y2 vector, then they're going to look like this: e to the lambda t times v1, that's this one, and t e to the lambda t v1 plus e to the lambda t times v2. So that's just both of these written out. Our general solution is going to be c1 y1 vector plus c2 y2 vector, just like it has been in the previous sections. But I think especially with this one, it's just interesting to see what it looks like as a solution matrix. So this thing, right? So I'm going to write these as vectors right? It's good to keep in mind that y1 vector and y2 vector overall, those are vectors, right? They're just, in this case, 2 rows, 1 column. So this first one, if I multiply it out, e to the 2t and 0. And if I multiply this one out, I get t e to the 2t, and then 0 down here, and e to the 2t times 0, so nothing gets added to this one, but e to the 2t is down at the bottom here. What that means for my solution matrix, again, remember my solution matrix, and then I have written right, just my general solution. My solution matrix just uses y1 and y2 as the columns of that matrix. So this is a 2 by 2 matrix where I use my solutions as columns here. And that's what that looks like here. Okay. So like I said, this is generally what you're going to have to do using that v1 and v2 vectors. This is generally what you're going to have to do for repeated eigenvectors, or sorry, repeated eigenvalues. And if you do it in that way, then you'll end up with 2 linearly independent solutions. You'll have a fundamental set, and you won't have to worry about finding the Wronskian of this or anything like that. You'll always end up with a solution that'll work for you. This last example that I want to do is another v1 and v2